All right, in this video, we're going to be working BC Homework 11.2b. Really just some more series work, but I think what's notable about this one is the first time we're going to be really using the limit comparison test, which is going to be one that's going to be very helpful for us. So we're going to start by using limit comparison to determine whether each series converges or diverges. All right, so first, we really just kind of want to think about what is the series like? What's the net difference in powers would be a good question to ask. So k over k to the 3, that's kind of like 1 over k to the 2. So okay, that's way too much pen. So I want the sum from k equals 1 to infinity of 1 over k squared for comparison. Okay, so if I'm going to do limit comparison, there's kind of 3 steps. First step is come up with one that we know. Okay, so this one is going to converge by the p-series test. So we need to say what happens and why. Okay, converges because p is 2, which is greater than 1. All right, then I'm going to do the limit work. So the limit as k approaches infinity of, all right, the terms that we're interested in divided by the terms of the series we know. Okay, and if you can just see it, then you can say that, okay, that limit's going to be 1, but if you don't, then you're going to actually distribute the k squared to the k, and get k to the 3 on top, and k to the 3 plus 2 in the denominator, and that's a limit we just need to know is equal to 1. Okay, and because that limit is positive and finite, so I'm going to say because I got that result, I know that our series A does the same thing as the series I brought in for limit comparison. So I'm going to say A also converges. Also, we always need to have that also part. It's like not part of the justification or anything. But if you make sure you always have the also, you never fall into that logical trap of saying, okay, well, if that limit was not positive or not finite, then they have the opposite behavior. We can't do that. Okay, so you'll never see me do any of these comparison tests where I don't have my conclusion say, this series also does whatever. All right, for B, I'm seeing a net difference in top and bottom 1 degree. So I'm going to say we're going to limit compare to the harmonic. So the sum from k equals 1 to infinity of 1 over k diverges because it's the harmonic series. Then we're going to do the limit comparison. So limit is k approaches infinity of k squared over k to the 3 plus 2 multiplied by, okay, dividing by 1 over k is like multiplying by k over 1. Okay, that limit's going to be 1 because I'm going to have 3 powers of k in the numerator, 3 powers of k in the denominator, leading coefficient of 1 on each. So that limit's 1, which I need to point out is positive and finite. And as a result, I can conclude that B also diverges. Okay, I know it says do the limit comparison test, but like what would we do it against? Like 1, I guess? That's a clearly divergent series, but we're not going to divide these things by 1 and find that we get a positive and finite limit. That's not what I'm going to do. So I'm just going to do the nth term test. So in this case, the kth term test, so the divergence test. The limit is k approaches infinity of k to the 3 over k to the 3 plus 2 is 1, which is not 0, and that gives me the divergence. D is a little bit more interesting. I've got the square root of k to the 3 plus 2. And so what you really want to do is kind of like simplify the situation in your mind. The square root of k cubed is going to be k to the 3 halves. So I'm going to limit compare to the sum as k runs from 1 to infinity of 1 over k to the 3 halves. Okay. This thing converges by the p-series test. And then we're going to do the limit comparison. Really, this whole exercise here is so that we do it the once and we know that, like in a multiple choice setting or situation where you just need to know whether it converges or diverges, we don't need to worry about, ones that are very close to P series, they're polynomial on top, polynomial on bottom. We can just pretty much treat them as P series, especially in situations where we don't need to justify our answer. But it's also good for us to practice that justification too. So 1 over the square root of k to the 3 plus 2 multiplied by k to the 3 halves over 1. Okay, that limit is going to be 1 over the square root of 1. Really, I guess. And that is a positive and finite number. And as a result, I'm going to say that D also converges. All right, here I've got just 3 series for you to look at, and just like which of these converge. And I also realized recently, it was pointed out to me by one of the students in my class, I hadn't been writing enough series out as, actual sums like this with it kind of spelled out terms and then a general term and the dot dot dots. So let's look at these. So if I look at Roman numeral 1, n is just an exponent, so that means it's geometric. And the ratio is going to be negative 1/4. So let's say geometric ratio equals negative 1/4, and the absolute value of r is less than 1. All of that points to convergence. Right, negative 1 to the n over 2. 1/2 minus a half plus a half minus a half plus a half minus a half. Okay, that's going to diverge. That's very much like that negative 1 to the n series. It's just half as much. And that's going to be kind of like oscillating, not settling on one number the more terms we add. So I'm going to say this one diverges by the nth term test. So limit as n approaches infinity of negative 1 to the n. That limit doesn't exist, and dividing by 2 isn't going to help that. And really, okay, the fact that that's not equal to 0 gives me the fact that this series diverges. And 1 over 3n plus 2. This is not a harmonic series, right? That I would need a half, a third, a fourth, and a fifth, and a sixth, and a seventh, in addition to the eighth, and also the ninth and the 10th. So this is not harmonic, so I can't just say diverges harmonic, but it is going to diverge like the harmonic series does. We're going to do limit comparison. So over here for number 3, actually I can probably fit it in. The sum as n goes from 1 to infinity of 1 over n diverges because it's the harmonic series. Do the limit comparison test. And as n approaches infinity of 1 over 3n plus 2 multiplied by n over 1, that's going to be 1/3. That's a positive and finite number. As a result, I'm going to say that, Roman numeral 3 also diverges. All right, we'll move on. So let s equal negative 1 to the n to the 2 over n to the 3 plus 1. All right, explain why we cannot use the comparison test with the harmonic series to show that s diverges. Okay. No, that's nice. Hey, it's not possible to show that s diverges because we're going to find out in the next lesson that it actually converges. But, we're just talking about the comparison test right here. All right. So I think if we think about 1 over n and the terms of this series, we're going to find that we don't have a consistent inequality. That would be why you could not use the comparison test. We look at it, we see it's bigger on bottom by 1 degree, but it's also got that negative 1 to the n. It's causing it to alternate, and we don't really know what that means yet. especially for the convergence or divergence, and we've got plenty of time to investigate that too. So I think what I'm gonna do is bring in a calculator. All right, so I've got the calculator. I plugged in f of x equals basically the terms of s, and g of x is the terms of the harmonic, the corresponding terms at least. I don't know why I called for that. I need a table, and I'll type in x1, and then I'm going to do f of x1, and then g of x1. All right, so I'm just going to do 1, 2, really. Let's see. Okay, that's much better. Okay, 1, 2, 3, and we can see. All right, so far the terms of blue are greater than the terms of red. Okay, okay, so G is the harmonic. So the harmonic series is greater. Continues to be greater. Okay, obviously it's greater in situations where the middle column is negative. But it looks like it's going to stay. Oh, yeah, it's greater, not less. So, yeah, if the harmonic series was the one that was the lesser of the two, yeah, okay, I'm satisfied. That's what's happening. If the harmonic series was going to be the one that was the lesser of the two, then, oh, and I see because that ended the 3 plus 1. That's the difference. Then we could say that S clearly diverged because the terms were, greater. But that's not what we're seeing. The terms series need to be less, just for direct comparison, than the terms of S in order to guarantee divergence. And then why can't we use the limit comparison test with the harmonic series to show that S diverges? Well, suppose we could. A little proof by contradiction here. I think that's going to be the way to go. We're going to do the limit as n approaches infinity of -1 to the n to the 2 divide by n to the 3 plus 1. Limit comparison test with the harmonic would involve multiplying by n over 1. Okay, we can see 3 powers of n in the numerator, 3 powers of n in the denominator, -1 to the n. This limit does not exist. And so that's specifically why. Or, I mean, if I really wanted to be even more specific, it's not positive and finite, right? I don't think I can write that, but that's what is true there. All right, so use the comparison test with the p-series to determine whether each series converges or diverges. All right, the comparison test. And, okay, yeah, I am going to leave the graph on screen. I just don't need that table anymore. All right. All right, now this first one, we won't need the calculator at all for. Natural log of n divided by the square root of n. Well, just think about 1 over the square root of n. That thing diverges, and the numerator stays 1 the whole time. But natural log of n, that's the type of function that grows. I mean, it grows really slowly, but it does grow. And so I can say that the terms of a are greater than the terms of the divergent p-series 1 over the square root of n. Okay, so I'm going to say let bn equal 1 over the square root of n. The sum of bn diverges, and I'm going to put the indices. P-series test, p equals 1/2, which is not greater than 1. Okay. I'm going to say if an equals log n over square root n. Yeah, and that's why n starts at 3. Okay, because we need log n to be bigger than 1. Okay, and log of e is equal to 1, so n equals 3 is the first integer after e that we can get the log of n greater than 1. All right, so I'm going to say is greater than 1 over root n for n greater than or equal to 3. As a result, the sum an also diverges. Oops, pardon me. I just kind of realized I lost track of how I usually justify my answer on direct comparison for AP Calculus. Kind of just like went at it and just said how I felt. I usually try to also do a 3 bullet point situation for this as well. Start off with what we know. Okay, so the divergent P series, I would write, okay, this series diverges, P equals 1/2 is less than or equal to 1. Then the inequality that I'm doing the comparison with, right? So that's going to be natural log of n over the square root of n is greater than 1 over the square root of n, because the natural log of n is greater than 1 when n is greater than or equal to 3. And as a result, a also diverges. Okay, so I like that method of showing our work a lot better. Okay, so I'm going to stick with that. I just forgot. It's been a while. So over here for b, I'm going to say sine of 1 over n squared. This is one that we used the integral test on. Yes. Okay, now also, the thing about direct comparison, or the comparison test, is we do need, like the terms. I don't think I can have the terms of the one I'm interested in going negative. But sine of 1 over n is going to stay positive because really I'm taking values of sine between sine of 1 and sine of 0, as n goes towards infinity. And 1 radian is well within the first quadrant where sine is definitely positive. Okay, so I'm satisfied. We showed that this one converged using the integral test in the last homework. And what I'm going to do is say, okay, well, I'm going to directly compare this one to P series with P equals 2. Equals 2, which is greater than 1. Okay, then I'm going to do the comparison. Sine of 1 over n squared is, less than, 1 over n squared. Okay, because the only time sine of theta equals 1 is that theta equals pi over 2. And or angles coterminal to pi over 2, but we're not going to be able to get that with 1 over n starting at 1 and going towards infinity. Okay, that's the inequality I need for n greater than or equal to 1. I think maybe I should have that this is positive. It's never going to actually equal 0. So let's say that. I don't know, that might help. And then as a result, b also converges. Because the terms of b are smaller than the terms of a series that we know to converge. For c, I'm going to have n over n squared minus cosine squared n. Alright. I feel like I'm supposed to be able to see something pretty obviously. Well, okay, cosine squared n is going to be a positive number between 0 and 1. In fact, I'm going to just write that in here. Okay, it's not going to equal 0 or 1 because integers, when we plug those in, we're not going to get, the type of transcendental number like pi over 3. You're not going to get those with integers. So I can't say it's a strict inequality for n greater than or equal to 1. Then, get rid of this. Let's see, I guess I'm going to say that, I'm going to compare it to the harmonic, because that one's, I think, the thing to do. And typically when you're doing direct comparison, you see trig, you're kind of just ignoring the trig. So n over n squared is equivalent to 1 over n. I'm definitely going to use the calculator for some support here. Okay, then, I need to hope that n over n squared minus cosine squared n. Okay, so I'm subtracting a number from the denominator, so I've got a smaller denominator. I still don't understand how this is going to work. A smaller denominator is a bigger result. So, how many of these terms are? I just am not seeing it as totally obvious to me. And these direct comparison ones are so frequently like multiple choice. We don't really have to justify our answer. So the whole justification thing on direct comparison is really pretty uncommon. I have seen it before, but not saying it's very frequent. All right, so I'm just going to do f of x equals x over x squared minus cosine squared x. Interesting function. Okay, so there is some place where that happens. I guess that's not totally surprising. Oh yeah, definitely. I can see there would be two places. And then g of x equals 1 over x. Okay, so there's a place where they're equal here. Then another place where they're equal. Okay, I need a table here. All right, so x1, f of x1, and g of x1. All right, so I'm over here at about 6. I saw there was an intersection around 1, so I'm just going to like 2, 3, 4, 5. So what happened? Originally, f was bigger, but then f looks like it continues to be bigger. It's saying they had intersections. I'm seeing consistently the column on the left is greater than the column on the right. Yeah, okay, and it was pretty far. I don't know what was happening on the graph. Why there were these multiple intersections, 4.7. Maybe they were tangent to each other again, because black has been consistently below purple on this graph. That is very interesting. Not really totally sure what's going on here, but that's how it goes with the series. It's an interesting topic. So, but I'm seeing that this is true. That over here I've got terms of the harmonic series in this column and terms of series C over here. So I'm seeing that inequality is true. So it must be that C also diverges. And that's also what might happen when you go just out searching on the internet for direct comparison infinite series examples and grabbing all the ones you like. And some of them are going to be a little more challenging than what we would typically see in AP Calculus. All right, now for D, I'm not going to need the calculator for that. I think I'm going to write out some terms of D. D is when n is 1, 1 to the 4 plus 2, 2 to the 4 plus 2, with 4 plus 2, that'll be plenty. Okay, I'm going to talk about this other series S, which is just going to be 1 over the square root of n to the 4th. Okay, if we look at S is equivalent to a P series with P equals 2. So I can say that converges by the P series to SP equals 2 is greater than 1. Then I can say, okay, well, the terms of S are greater, the terms of S are greater than the terms of D, right? Because we've added into the denominator, so the terms of D, I think a better way of saying it, are even smaller than the terms of S, so series D must converge as well. Okay, Then, so my second bullet point, the kind of the inequality I want to make is that 1 over the square root of n to the 4 plus 2 is less than 1 over n squared for all n greater than or equal to 1, and as a result I'm going to have d also diverging. All right, then we're going to use the comparison test with a geometric series to determine whether each series converges or diverges. All right, so that's a lot of direct comparison, but that's what I did this on purpose, right? And that's why I'm slowing down this class to do 2 days for 11.2 and 2 days for 11.3. So we can get as much practice in as we need. So I'm thinking, okay, 2/3 to the n is compared to, so 1 to infinity of 2/3 to the n converges. It's geometric with r equals 2/3. And what's relevant about that is that the absolute value of r is less than 1. Okay. Then I need an inequality. So I need really my terms. Oh yeah, I see why that would be the case, because it's addition, are smaller than the terms of a. So that would be 2 to the n over 3 to the n, right? Because I've added that number to the denominator for n greater than or equal to 1. As a result, a also converges. All right, with this next one, it said just with the geometric series, and e to the negative n is a convergent geometric series. So I'm going to say e to the negative n converges. It's geometric with ratio equaling e to the negative 1, which is 1 over e, and the absolute value of r is less than 1. Right, now I'm going to do the inequality to compare the two. So yeah, e to the negative n divided by n squared, if I'm dividing by a number that's greater than or equal to 1, yeah, that's going to be less than or equal to, it's only equal at n equals 1, e to the negative n over 1, for all n greater than or equal to 1, then as a result, I can conclude that b also converges. Let's see, 1 plus cosine n over 2 to the n plus cosine n, geometric series. Understand if it's 1 minus cosine n. Let's see. Oh, okay, again, this is another one I got off the internet, and I see what I need to do. Okay, this is going to require a level of creativity that I do not think that AP Calculus requires. Also, you could just say cosine of n does not really grow, so this is very similar to 1 over 2 to the n, which is a geometric series that converges, and I actually think limit comparison is the way to... No, I don't know. Maybe it is direct comparison, but what I'm saying is we're going to directly compare to 2 over 2 to the n. All right, so I think what I'm going to say is that 2 over 2 to the n equals 2 times 1/2 to the n. Okay, so that's how I know that the series 2 over 2 to the n is converging. Its geometric ratio is 1/2. So I'm going to say my first point is that the sum from 1 to infinity of 2 over 2 to the n converges. It's a geometric series with ratio equal to 1/2, and what's relevant about that is that the absolute value of r is less than 1. Okay, then I'm going to do the comparison, the inequality. I'm going to say I need 1 plus cosine n. Yeah, that's the thing. So at most, cosine of n is equal to 1. It's never going to actually equal 1 because that would happen at 0, pi, 2 pi, and so on. So we missed our chance for it to actually equal 1. That would have been an n equals 0 only. That would be the only integer that works. So 2 to the n is less than 2 over 2 to the n for all n greater than or equal to 1. So as a result, I can say that C also converges. Okay, then for D, I'll use the comparison test just for the sake of argument, but and showing you one that diverges, but this is not a good example of one that diverges because you can use the divergence test. The limit of these terms is clearly non-zero. Okay, this fraction is bigger on top. The top is growing faster than the bottom with no doubt, so the terms aren't even going to 0. D doesn't have a chance to converge. We already know it diverges, but I'm going to say 5 halves to the n diverges because of being geometric with a ratio too big. Then the comparison is going to be n squared plus 5 to the n over 2 to the n is definitely greater than 5 to the n over 2 to the n for n greater than or equal to 1. And then as a result, D also diverges. Right. Now this one is another problem that we had on the previous homework, but now we're going to apply our new techniques and it's going to take a whole lot less space. We're not going to have to do the integral test for part A, right? We can see that the denominator has degree 1 greater than the numerator, so we're going to limit compared to the harmonic. So I'm going to say the sum from 1 to infinity of 1 over n diverges because it's the harmonic series. Then I'm going to do limit comparison. So that's limit as n goes towards infinity of 4n over n squared plus 1 divided by 1 over n is multiplying by n over 1. That's equal to 4. That's positive infinite. And as a result, we have A also diverges. Now we've got a rule for B, or the terms of B. Okay, terms of B are the terms of A divided by 2n. Okay, so I'm going to do a little bit of algebra first. Say Bn equals 4n divided by n squared plus 1. Divided by 2n is like multiplying by 1 over 2n. So I'm going to say that's 4n divided by 2n cubed plus 2n. Okay, so this one's bigger on bottom by 2 degrees, so I'm going to limit compared to 1 over n squared. Okay, they asked about, I haven't mentioned that in this video, is that they're asking, it's starting from n equals 1, so I need to compare starting n equals 1. 1 over n squared converges by the p-series test. And I'm going to do the limit comparison as n approaches infinity of, if you want to say bn divided by n squared, like, be my guest. Bn divided by 1 over n squared. Okay, don't say it divided by n squared, that would not work. But I think the safest course of action for us is going to be to write it out to convince ourselves of the limit. If you think the limit's going to equal 2, it does, but it might be best for us to just write it out so we don't say anything wrong. Okay, so dividing by 1 over n squared is like multiplying by n squared over 1. Yeah, I'm going to have 4 into the 3 divided by 2 into the 3. That equals 2, which is positive and finite. And as a result, B also converges. Right, another one. In the last homework, we used the integral test to show that Tanner converged. Okay, so we're going to use a direct comparison to show that Tanner converges, and then we're going to use limit comparison to show that he converges as well. All right, so use direct comparison. So, all right, we're going to compare it to the p-series. So from k equals 1 to infinity, and we use the integral. Yeah, we used the integral test, and that was kind of involved. But and I think I only gave that series a name. The very first year I taught the class, forgetting about the limit comparison test, and I think I kind of forgot about the limit comparison test again this year when I had mentioned that to y'all. At least in class this year. 1 over k squared plus 1. Wait, no, that's what I'm interested in. I'll get there in a minute. So 1 over k squared converges because p equals 2 is greater than 1 again. Then we're going to do direct comparison. The terms of 1 over k squared plus 1 are properly less than the terms of 1 over k squared when k is, t starts at 1, so k greater than or equal to 1. And then, as a result, I know that t also converges. Okay, then we can also use limit comparison with the same series. I'm going to just make use of copy and paste, because it's going to start off the same way, but then I need to do my limit work. Limit as k approaches infinity of 1 over k squared plus 1 divided by 1 over k squared. That's going to equal 1, which is positive and finite. So if you start writing finite, you might as well just say finite and positive. And we can say, as a result, t also converges. This one is from, oh yeah, it's one part of a free response question from 1974. Does this one converge or diverge? Justify your answer. So we can use limit comparison test on this one. So I know that n equals 1 up to infinity of 1 over square root n diverges by the p-series test. Not greater than 1. Then I can do some limit work. Okay, that's going to be, really I take the fastest growing thing in the numerator and the denominator. I do the AP pre-cal thing. Okay. We can do that. That's the square root of a half, or 1 over the square root of 2, or root 2 over 2, whatever you want to call it. It's got to be some correct number. I think I would call that 1 over the square root of 2. Yeah, you could say that's square root of 1 over square root of 2. That's that number that's the sine of pi over 4. There's many different forms of that number. This result is positive and finite. And as a result, our series that we don't have a name for, this one also diverges. to the n minus n. Why can't we use direct comparison to show that r converges? Yeah, and then we'll need to use limit comparison. Okay, the reason why is that the inequality isn't going to hold. Yeah, because we're subtracting in the denominator rather than adding, because if we wanted to show convergence, we would need the terms of r to be even less than the terms of this geometric series. And that's not what's happening. It's less in the denominator, which leads up, that's a greater result. All right, so 1 over 4 to the n minus n is actually greater than 1/4 to the n, which is just 1 over 4 to the n. But we would need the inequality to go the other direction. Okay, but that's the main reason. And we're going to use limit comparison to the geometric series. So this one converges because it's geometric with r equal to 1/4 and the absolute value of r less than 1. Then limit comparison, limit as n approaches infinity, of 1 over 4 to the n minus n, okay, divided by 1/4 to the n. Okay, well that's 1 to the n over 4 to the n, but 1 to the n is just always 1, so this is going to be 4 to the n over 1. Okay, that's going to be a limit of 1, because the fastest growing thing on top and bottom is the 4 to the n and the 4 to the n. Okay, divide that by itself, you're going to get 1. Okay, but this result is positive and finite. And I can say that R also converges. All right, and then number 10, is that it? Or no, there is another problem. I don't know where this file came from. I know that, I'm pretty sure the one that I passed out, the copies, there's a number 11, and there's intended to be a number 11, so I'll just go look at what it's supposed to be and do that at the end. Okay, determine whether each series converges or diverges, justify your answer, 8 of them, yeah, that's what we need. All right, so for A, that's limit, like it's the same degree on top and bottom, so it's like, wait a second, it's not even bigger on bottom. These terms aren't even going to 0. I'm going to use the nth term test. Limit as n approaches infinity of 3n over n plus 2 is 3, which isn't 0, so that gives me divergence. Right, for B, 3n over n squared plus 2n. If any of these are like polynomial on top, polynomial on bottom, we just go ahead and use limit comparison test. So like up to C, we're going to be using a limit comparison test. D, that sine of the absolute value of n. Why would I need the absolute value? I think that's supposed to be the absolute value of sine n. Yeah, I'm going to change that. Yeah, and I think for pretty much all of these, except for any of them that are like kind of legitimately different or interesting, I'm gonna maybe like for B and C, I hope you'll forgive me, I'm gonna say for B, limit comparison to harmonic. We have done more than enough practice on our justifications, and if you've done all the problems with me up to this point, feel free to say limit comparison to harmonic, because it's bigger on bottom by 1 power. That is going to give me divergence. For C, we're going to do limit comparison to 1 over n squared. But don't write limit comparison to 1 over n squared. That wouldn't make sense. It would be the sum from n equals 1 to infinity of 1 over n squared. And that would give me convergence. Okay, that's that kind of terms versus total thing that is critical to our understanding and also our getting credit for justifying our answer. All right, for D, I am going to need a direct comparison, but I'm just going to kind of say, all right, absolute value of sine n over square root of n to the 9th. That's going to be less than 1 over n to the 9 halves for n greater than or equal to 1. And then we also have that series 1 over n to the 9 halves converges by the p-series test. And so as a result, I've got convergence. Okay, for E, I would be doing limit comparison to, let's see, this is kind of an interesting one. So 2 powers on top, 7/3 of a power on bottom, so n to the 2 divided by n to the 7/3. Well, 2 would be 6/3, so n to the 1/3. Okay, yeah. So I'm going to say limit comparison to that series. The sum of 1 over n to the 3, or 1 over 3. Okay, that's going to give me divergence. Right, f 4 to the n over 2 to the n plus 3 to the n. Okay, that's one that does not converge. If you said the limit of the terms was infinity because the numerator grows faster than anything in the denominator, that would be true. What was I gonna say about this one also? You could do a limit comparison to 4/3 to the n. Like, so you'd have a 4 to the n in the denominator and a 3 to the n in the numerator, producing a 12 to the n in top and bottom, and that would have limit 1. But I think the best would just be if you understood that because 4 to the n grows faster than 2 to the n or 3 to the n individually, as n approaches infinity, this ratio is going to approach infinity. And because that limit is non-zero, that's going to give me divergence. And then g, 1 over 4n minus 1, we're going to limit compared to the harmonic and get 1/4, which is positive infinite. We've done plenty of that. That is diverges. And then h, 1 over n natural log n. Okay, so if you remember, that's one of our named series. We know that guy diverges. But maybe if you just were out or you just flat weren't paying attention or didn't get it the first time, I'm going to do the integral test. Okay, so for the integral test, first we got to check the conditions. We're going to remark that the function we're going to be taking the integral of is continuous, positive, and decreasing. I like to point out where, like, that's the truth, because that's going to be the interval on which we're adding as well. Then I'm going to set up my improper integral to be the limit as b approaches infinity of the integral from 2 to b of 1 over log x times x dx. And I like to put the x second. Hint at the fact that we're going to be doing some u substitution. Now, if I'm doing u substitution with an improper integral, I'm just going to recommend you go off to the side and just do the anti-differentiation. So I'm going to use u equals log x and du equals 1 over x dx. Okay, so that'll be integrating 1 over log x times 1 over x dx, which is going to be 1 over u du. Okay, that antiderivative is the log of the absolute value of u equals log x, so I have log of the absolute value of log x. Okay, it's weird, but I can work with that. I'm going to have a limit, okay, this limit on the left is equal to a limit as b approaches infinity of the difference of what happens when I plug b into my antiderivative minus what happens when I plug 2 into my antiderivative. So I might copy in the antiderivative and then plug in b and 2, and then start to think about what happens as b approaches infinity. This limit is not going to exist because as b approaches infinity, so does the natural log of b. And on the inside of that absolute value, okay, the argument of the second, the outermost log, the argument's going to infinity, so the log itself also goes to infinity. So this limit does not exist. That gives us the divergence of h, and there we go. All right, the last problem we've got is if the limit of an is 5, which normally would have us thinking that the sum of an diverges by the divergence test, does the sum from 1 to infinity of an over n converge or diverge? And that's an interesting question. I would think that we couldn't tell necessarily, but I'm going to do limit comparison against the harmonic. Yeah, I'm going to do limit comparison against the harmonic because what else can I do? And I think I'm going to get a limit of 5. So I'm just going to say the sum as n runs from 1 to infinity of 1 over n diverges because it's the harmonic. Then the limit as n approaches infinity of an over n times 1, times n over 1, because I'm dividing by 1 over n. That's going to equal, just the limit of an, which is equal to 5, which, is positive and finite. And as a result, our series that we're interested in, definitely diverges as well. All right, so that was another really long homework. So that's all I got for you for this video. Thanks for watching.